Hello, welcome to Intro to Machine Learning, DS 4400, Lecture 13. So, this is a class at Northeastern University. And today we're going to continue with the theme of supervised learning, as well as specifically on the topic of classification. And more specifically, we're going to talk about logistic regression. It's just one of the most basic ways of doing regression. Sorry, classification. Classification. Anyways, so for classification, we previously learned the concept of regression, right? And in regression, we're predicting some number within a range of numbers, like the age of somebody, or the housing price, the stock price. Now, today, we're going to transition into classification. In classification, what we do is instead of predicting a specific number within a range, we are predicting categories. So, examples is this picture of a dog or a cat, right? So, yes or no. Which letter is the picture showing, right? Any letter within the alphabet. Does patients have cancer? Yes or no? So these are like categories which we're predicting instead of a particular number. In classification, we have a finite number of possible categories, and we want to pick the correct one. And in the simplest form of classification, it's called binary classification. In binary classification, basically your choices are just two possible outcomes. Yes or no, right? Does he have cancer or not? Yes or no. Is this a dog or a cat? Yes or no. And the way we represent them is through two ways. One is either 0 or 1, right? So those are the two categories. 0 as like the first category, and 1 is the second category. Another way we like to represent the labels is -1 and 1. Hmm? But in either case, right, it's just two options. Now, one of the most popular function we use for classification is the sigmoid function. Right? It's commonly used for binary classification because you put in some x value. Right? This is the shape of a sigmoid. So you put some x value and you give you a y value that's between 0 and 1. Right? We put another one here, which is pretty close to 0. We put another one here, that is 0. Put another one here, that's 1. So when you're trying to predict binary things, where it's either 0 or 1, it makes sense that you put your value into a function such that the output is constrained within 0 and 1. Right? That's why sigmoid is a really popular function. The sigmoid is useful because it forces the output to be between 0 and 1. It gives us a clear way of choosing yes or no, right? For example, if our output is less than zero point 0.5, then we're going to pick 0 and say the answer is no. Or if it's greater than zero point 0.5, like right here, 0.5, is greater than zero point 0.5, then we're going to pick yes. Therefore, the output of a sigmoid function can be used to determine binary classification problems. Uh, Now, we have previously gone through the sigmoid function when we're doing like derivatives, and now you're starting to see why this function might be important. Sigmoid function. Since the output of a sigmoid function is between 0 and 1, we often interpret the output as probability of a yes event. Okay? For example, does this person have cancer? 0 as no, 1 as yes. If we get a sigmoid of output 0.2, we can interpret it as the probability of yes, right, is 0.2. The probability of no is 0.8. Therefore, it's more likely that it's a no. Let's assume that the truth of this person does or does not have cancer is therefore the probability should be 0. So let's say this is our prediction and this is the truth. The truth, there's no ambiguity. It's either no cancer or yes cancer, right? So we can see that what we have predicted is like a binary probability. Here we go. And the truth is yet a different probability. Okay, so this is like a probability distribution. This is also like a probability distribution. Now, if we have two distinct distributions, right? One distribution is the one we predicted, and the other one is the truth, right? What we could do now is we can measure how close we are to the truth, right? We can measure the error of our prediction. Now, we went through the last class specifically for this purpose with information theory, right? We can measure the error, which is the difference between distributions. Now, we can do this, right, assuming that we have two Bernoulli distributions. The standard method is to use this thing called cross entropy. Now, we went over the last class what cross entropy is. If you have cross entropy of P and Q, it's essentially measuring their difference, right? You want the cross entropy to be basically as small as possible. And then that means they are essentially the same, or as large as possible, implying that they are very, very different. You may remember the equation from the last class, right, for cross entropy as this, right? Cross entropy is essentially the average information of Q using P as the probability. The average information of Q using P as the probability. So, alternatively, is the expected information for Q, given P as the probability. So like that was from last class. And the idea of it was that we could use cross entropy to measure the difference between two distributions. So over here, you can see that the difference is not that big, right? This part is very similar. This part comes out, and this part is 0. So therefore, it implies that we can measure error using the cross entropy. Right? What we do is we call the true distribution as P of x. So that's the true distribution. And we can just let our predicted distribution be Q of x. Then the error between our prediction and the truth can be described with this equation. Now, if there are two samples, because because this is Bernoulli, so there are two options. That's where the sum of two is. So I mentioned previously that the mean square error is probably the most commonly used objective for regression, but cross entropy is the most common objective used for classification. So practicing calculating the cross entropy. So let's say we have, this is the situation we are talking about. This is our prediction, and this is the truth, right? And this is like we can also treat this as a Bernoulli distribution. So the error, right, is then follows the cross entropy. So if we were to write out the entire cross entropy, it would be the probability that the event is cancerous, right? Times that QE is cancerous. So notice how we're following this equation. And then plus the probability that it's not cancerous for P, yet and it's not cancerous for Q. Okay? So it's going through the two possible events. And then you can see probability that it's cancer as the ground truth is 0. Right? It's 0. And since it's 0, this whole thing is 0 now. And therefore, it's the probability right here. It's the probability that you don't have cancer times 1. And that's our error. Now, this is a case where there is an error. So what if there is an error that we actually made a perfect prediction? Well, if it's a perfect prediction, then this would still be 0. But we would predict 1 here. If we predict the 1 here, 1 over 1 is 1, right? Therefore, e to the 0 is equal to 1. Therefore, our error is 0. So you can see that with cross entropy, the error of a sample, right? If you make the perfect prediction, it heads towards zero. And as the error gets bigger, you can see that it gets bigger and bigger. Now, calculating the cross entropy error with multiple samples. So this example here, we just showed you, was with one single sample, right? But in an experiment, you have like n number of samples. So it could be, you have to add them all up, right? So in real life, we may have thousands of millions of samples. In those cases, we normally calculate the average error from the samples. So we calculate all the errors and then average them together. So let P1, P2, P3 be the probability, the true probability distribution from the samples. And Q1, Q2 be the predicted probability from the samples. Then the average cross entropy error will essentially just be the average cross entropy, right? And then the P and Q will go from 1 to n. Now, when you do this, we just plug this into here. So this right here, this right here is the cross entropy for one sample. And then we're going to essentially average out n samples. Now, since this is a binary case, then it's just the first case, second case, and them add up together. And that's it. This is the error, right? The average error. So this is actually the objective we would be using to minimize the error. We're trying to minimize this error. So in this example, new example, we have three samples, and we will essentially calculate each individual error and average them together. So remember, I was saying 1 to n. So here, n will be 3, right? It will average them together. The whole algorithm, now let's take a step back. Remember, the whole algorithm started when we were talking about this like sigmoid function, right? Because the sigmoid goes like this, between 0 and 1. Now, since the sigmoid output is always between 0 and 1, we're treating it as a probability Q. So this is Q is the output of our sigmoid. So right here, Q. So this right here is our probability distribution. Now, theta, we don't know. We know that if we put x in, it's going to give us some Q. So the idea is that given some input x, we want to predict the probability of certain event E. Theta are the unknown variables but that if we can find them, you give us the exact probability distribution. I shouldn't have written exact, approximate. For now, we don't know theta. Now remember, we previously learned a bunch of distributions which all had the theta parameter, like this, right? So for example, this was the exponential. So the exponential distribution had this phase, and that was our P of x. Now, instead of this distribution, we're going to use this one instead. If we continue with the previous example, assuming like we have the two blood tests, right? Assuming we're taking two blood tests, X1 and X2. Based on these two blood tests, we want to identify if a person has a certain cancer. So how will we go and do that? Well, then Q event that it is equal to cancer is equal to this. Remember, that was the sigmoid, and we don't know theta. And the Q probability that there isn't cancer is just opposite, 1 minus the probability that is cancer. Therefore, 1 minus this here. Okay, so notably, that probability that isn't cancer is just 1 minus the probability that there is cancer. So now we can plug this probability, right, into the error equation. So now we're going to plug this Q of E into here. Right? So you can see this actually is a function of theta. So there's a theta in here. right? So if you write the whole thing out, it looks like this. So the average error, okay, let me write this out. So here's the Q of E with Cancer, Q of E without Cancer. So I'm gonna plug them in here, right? And I'm gonna plug them in here, right? I just plugged Q of E with or without Cancer in. So now we have equation, right? This right here is the equation that has theta inside and represent the average error. So what we know now is we have Q. Q is this. Currently, we don't know theta. But once we find theta, this means we can just plug X in and it would tell us the probability of cancer events. Okay? Cancer. Now, so this is what this equation, this is like in practice, after you find theta, this is what you will use to make predictions. But in order for us to find theta in the first place, the objective we're trying to minimize is the average error. Okay? So the average error is therefore this entire equation, which we just previously derived. The only thing missing now is that we don't know theta. So ideally now, how do we go find theta? Well, we find a theta that essentially minimizes the average error. And to do minimization, I already showed you guys how to do that, right? Gradient descent, right? If we do gradient descent, we just need to take the derivative of this. At this point, I would like to think that you guys have done enough practice so that you have confidence you can find the derivative. But even if you don't, you get the point that essentially where this logistic regression objective came from. Yeah, this is the logistic regression. And then once you have this objective and you can find the derivative, you can now follow the gradient descent. That probably should be negative, right? That's a negative. Okay, so that was a mistake. So gradient descent algorithm, right? Where the current one subtract the gradient, you get the next one. So you see here, this is why I really emphasize on you guys knowing how to take the derivative of sigmoids early on. Like if you pay attention back then, you will now see that this is yet just another iteration where we have an objective and we're trying to minimize it. Once we minimize it, then we can essentially make predictions. So in machine learning, right, this actually happens over and over again. It's a very common theme, right? Essentially, a lot of the algorithms will require you to perform gradient descent. You can always perform gradient descent if you know how to take the derivative, right? Now, equation one, what we show here, is logistic. This is the logistic regression. And this is one of the most basic, right, classification technique in machine learning. Now, once you find the theta, right, then you essentially have a prediction probability, which you plug X in, it will tell you the probability that you have cancer. Okay. Now, the derivative of the logistic regression, I hope you can do it, but we'll do it together. Like, we'll do it together here. So, objective. So, here's the objective. So, first, we're going to try to simplify it because there's a lot of complications in here. So, let's see. Well, this is 1 over this, right? So I can just move this to the top. That's how I get this part. This part here, well, I could move this to the top. Okay, I see. So what I did is essentially this right here could be written as 1 plus e to the minus x transpose theta, 1 plus e to the minus x transpose theta. So this is equal to 1. That's where the 1 came in. And if I subtract 1, 1 plus e to the minus x transpose theta. All right, that's how this is how I essentially get this expression. Now, once I have this, we now have to use a bunch of log rules. Okay, so right here, division, I can split the division into subtraction. So log allows you to split them. So that's how I did the split. After I did the split, let's see. What did I do? Oh, yes. This I can combine together. So that I combine that together. And then here is for this part. Let's see. This part. Oh, yes. Event 2. So PIE2 is equal to 1 minus PIE1. So because it's binary, right? So it's the opposite. So I'm going to write 1 minus PIE1. And I will get rid of the E and the log. That give us the exponent, which is right here. So that's what I did there. And then, let's see. I multiplied this on both sides, which you could do. So now I have on both sides. Interesting. So for this one, I took the exponential again. So if you take the exponential log, they will still be the same. This allows me to combine this and this because log of addition is equivalent to multiplication. So I multiply this here, which give us this term. And that's it. So this is the simplified version. So we had this like really complicated version, which is like, yeah, we don't want to take derivative of that. We want to take derivative of this. So now that we have this version, we're ready to take the derivative. Now, if we use the chain rule, right? What we use the chain rule first, we will do is this one. So log is 1 over this. And then, so 1 over this, we got that. That's from the log. Then we take the derivative of this, which is just itself. And then we take the derivative of this, which ends up here. Okay, so that was easy. For this part, we take derivative with respect to theta. Theta goes away, and that's what we have. Okay, so far so good. Now, I can, yes. What can I do? Okay, I can move the xi's out. So let's move that out. So that's how I got the xi. And then I multiply by 1. So once you move out the xi, which is this term, I multiply by 1. And why did I want to multiply by 1? Oh, it's because then this becomes 1. And this part here becomes this. So you can see this times this, which is this. And then this times this. 1 is minus, 1 is plus. They cancel each other out, which is then results in 1. So now this is a pretty simple form. So this is the derivative, right? This is a derivative we would normally use to solve the logistic regression. Now remember that, for example, if we had dimension for 3, then the gradient descent, this should be a minus. Gradient descent will have this equation. Now, if you think about it, the logistic regression is quite an accumulation of everything we learned this semester, like all the matrix and vector operations, right? Matrix vector type of calculus, like the idea of optimization, specifically minimization, supervised learning, how it divides into regression, classification, and then probability theory, like all the things we learned in terms of probability. like like information theory, cross entropy, all the notations, conditional probability. So in you knowing how to do logistic regression, this is essentially this is essentially how far we've come. Like it's about halfway throughout the semester, and we've done quite a bit uh, already, like so far. So let's move on. In binary logistic regression, right? Like I told you, the sigmoid can be treated like a probability distribution. And once we find the theta, then we know this distribution and we can plug x in to tell us the probability of particular events. So logistic regression give us a recipe on how we can use the data to find theta. Essentially, what we want to do is minimize the cross entropy between our prediction and the truth, right? We want the error, the difference between our prediction and the truth, which is the error, to be as small as possible. Now, then given n samples, then what we want to minimize is the average error. And then we use gradient descent essentially to solve it. Now, the reason why we're spending so much time with the details of logistic regression is because, first, it's a very basic machine learning technique that, like higher level technique, will assume you know how to do this already. Also, in many machine learning methods, like we use the same idea, right? You model the likelihood of event with some probability distribution, like this. Here, we use sigmoid, but we could use anything else. Or you can model an equation that looks like this, which is the result of regression. So anyways, so the model normally will have some kind of parameter. So those are the two cases I'm talking about. This is when we're doing regression. We don't know the function that we're looking for, but we make guesses on what the function will look like, and we try to find the best combination of these functions. So that's regression. And then with classification, then with the cross entropy, we're essentially predicting the probability of categories. So if you have category 0 and 1, in which we're going to predict the probability 0. 0.2, 0. 0.8. Okay. So and in order for us to make that prediction, we need to know the probability distribution. We need to know this function. But we don't know the function. So we find the theta that give us the best function that minimizes the error. And the error comes from the cross entropy. Now, this pattern where we don't know the function, whether it's probability distribution or the function for regression, this pattern that we don't know the function and we need to use some basis function in order to make the best guess, right, is the basis of a lot of machine learning algorithms. Like support vector machine use that, like linear polynomial regression, principal component analysis, linear discriminant analysis, and so many more. So 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 the pattern I hope you will recognize is, chances are we're trying to make some prediction. In order to make that prediction, we need to identify a function where we can put an input that give us the desired output. But to find this function is really hard, right? Whether it's a probability distribution or some other function. So what we do normally is we come up with a set of possible functions you might use, or a set of like a function that you think might look like that. And then we fill the parameters, theta, or in this case, ABC. So I hope you get the point. I would like, for this practice, I would like you to practice logistic regression. And essentially, given the data, it's only 4 samples. So you're supposed to group them, like separate them, right? So do the best you can to see if you can write your own gradient descent algorithm to separate, to like identify one is zero, the other one is one. Okay. Now, I have given you the code. I wrote the code for you guys already, which is right here. Do not, do not look at the code. Really, really study the math first. See if you can use the gradient descent. You run the gradient descent yourself. If you get stuck, then you can look at the code. Okay. So the first one I want you to do is with this simple data for binary classification. But the second one I want you to do is a very famous like data set called the breast cancer data. And it performs binary classification where you predict yes or no, right? So the way you can load that data is through sklearn directly. And when you load this data, you can write data.data. So this is the actual data. And then the shape of the data is 569 samples and 30 dimensions. Okay. Now the data target, the shape. So this is the label, right? Looks like this. So there are 569 labels, which makes sense because there are 569 samples. You can find out even the feature name. So what each feature means, like the texture of the cancer cell, the perimeter of the cancer cell, the smoothness, like all these things is what could go into a decision in predicting a cancer, right? So you can these are the feature names and these are the target names. So zero means is bad, and one, I think zero is bad, one is good. I think. Okay, so um, like I said, I wrote the code for you already, and so this works. But don't look at the code. Just do the best you can to see if you can reproduce it like yourself. Um, let's see. And lastly, if you so in this over here is the code that I wrote that uses gradient descent with logistic regression objective. Okay. Over here with NumPy, you can actually this is no with sklearn, you can just call logistic regression and you will solve it for you automatically. So you don't have to run the gradient descent. But the whole point here is for you to know what's under the hood. So see if you can run the gradient descent. And I think that's it. I will see you in the next class.